Good morning, everybody. Welcome back to Real Analysis. Apologize for starting a couple minutes late here. Hope you all doing well. Hope you all had a good first couple days of class. Plan for today is I'm going to kind of wrap up our discussion from Wednesday's class of the true-false activities. And then we're going to start talking about what are going to be our axioms for the real numbers. Today mainly focusing on what are going to be our cast of characters for the semester. What are kind of the different sets of numbers like the rationals, the reals, the integers, etc. that we're going to be working with going forward. And I know I said I was going to have a homework one for you all today, but after kind of thinking about it the last couple days, and especially because a large group of people are going to be gone, I decided I'm going to assign homework one on Monday instead. So I'll assign it on Monday. You'll have about a week to work on it, and things will be peachy from there. So with that, does anybody have any questions or comments before we get started for today? Why are calendars always so nervous? It's because they know their days are numbered. Okay, so last time, if you recall, we kind of went through, talked through the first 5 true-false questions as a class. You all decided that the sum of 2 real numbers must be a real number, that every positive real number does have a square root, that there does exist infinitely many real numbers between 0 and 1, and that if you have 2 unequal real numbers, you can always find a real number in between, but when we substituted the integers for real numbers, you all said that that no longer is going to be the case. So we're going to kick things off today with number 6. Where I asked you all to look at the question, does every function from the reals to the reals have to be continuous at least one point? Or is it possible to have a function that is continuous absolutely nowhere? So what did you all think about? Oh yeah, I forgot we were doing thumb votes. So thumbs up for I think this one is true. Thumbs down for I think this one is false. Thumbs sideways for I have no idea. Okay. So, a few question marks, a couple thumbs downs. That looked like mostly thumbs down?
Mostly thumbs down.
Okay. Mostly thumbs down, like Russ?
I think it's possible, but I can't prove it for the life of me, and I'm not sure why I think that, so
It's kind of hard because in Calc 1, you see in calculus classes, you tend to see a lot of functions that are maybe discontinuous at like 1 or 2 or 3 points. Like maybe the limit from the left and the limit from the right are different, there's a hole in your function, jump discontinuity, lots of ways a function can fail to be continuous. But the thing about most of those functions you probably have seen before are, they're continuous basically everywhere except at a small number of points. So, question is it possible for a function to actually be continuous at 0 points?
Could you just do like an infinite piecewise function?
An infinite piecewise function?
And just make it so like it's gonna hit all the reals? Where just by like going like up and down or just like craziness?
Just like craziness, like specifically saying, alright, at x equals 1 I want a y value of 2. At x equals pi I want a y value of 0. At x equals square root of e over 17 minus 15 billion 0.81 I want it to have a y value of, I don't know, e to the power of pi to the power of e. Do something like that?
Yeah.
In theory, you absolutely can. This one is indeed false. Here's a simpler function though, that can do it without having, that I can actually write down and say a finite amount of time. So what do we mean when we say if x is a rational number?
You can write it as a fraction.
Yeah, you can write it as a fraction, like 2/3 or 1/9 or -5 over a billion would all be examples of rational numbers. So if we take a real number and say, if we can write it as a fraction, map it to 0. If we can't write it as a fraction, map it to 1. What do you think the graph of this function would look like?
I mean, it would look like probably two lines, but they're not continuous lines. You can't zoom in far enough to see the breaks.
Exactly. It would basically look like except infinitely dotted lines, where you're constantly jumping back and forth between 0 and 1, and no matter how far you zoom in on the graph of your function, you're not going to be able to zoom in close enough. Turns out this is not continuous at a single point. That there's not a single point where you can zoom in close enough to the function and see, oh yeah, it looks like a nice smooth curve, or a point where you could take a limit and have the limit exist from either the left or the right-hand side. Bless you. So, this function has a special name. It's called the Dirichlet function. And I bring it up because it is a function, it is an example of how a function can be pathologically bad. Here's a fun fact. Let's say that there is a giant box containing all possible functions from R to R. If I were to pull a function at random out of that box, what do you think the probability would be that that function is nowhere continuous?
It's got to be like infinitely small, right?
Is nowhere that it's nowhere continuous? Turns out you're absolutely right. Except you flip it around, because there's a 100% chance that that function I pull out of that box is nowhere continuous. So what does that mean? There's a 100% chance. That means it's impossible to pull a continuous function?
Shouldn't it mean that there's like infinitely more totally, completely discontinuous functions than continuous ones?
It means that there are way more completely discontinuous functions than there are functions that are continuous at even a single point. It's just that when calc classes, etc., we like talking about continuous functions because those are things that are easier to work with, easier to, say, visualize. Because as far as completely discontinuous functions go, this is about as nice as you get. Most functions that are completely discontinuous are going to be, Matthew, like the one you kind of asked about earlier. Functions where it's just like, oh, you define at each point it's something completely random and the graph is just a giant jumbled mess of points.
Is it because you're kind of you're not treating it as like f of x is equal to x squared, you treat it more as like, we're just gonna randomly map this number to this number instead, and if
Correct.
you treat it that way, then it's gonna end up being more of, it's gonna be so impossible for these numbers to line up next to each other.
Pretty essentially, yeah. This is actually going to be very much related to number 8 here in a second. But yeah, if you were to take a function at random, it's very unlikely that real numbers that are close to each other are going to map to outputs that are close to each other. So, I don't know, that's kind of a fascinating fact, I think, and something that we're going to be exploring more throughout the semester. By the way, you all are going to have a future homework assignment, like halfway through the semester, to actually prove this is nowhere continuous. We're not going to prove it for now. But the idea is basically pick any x value, no matter how much you zoom in on that x value, you're always going to get infinitely many points that have a y value of 0, and infinitely many points that have a y value of 1 close to that x. I say close, air quotes. How about number 7? Every continuous function must be differentiable at least one point. Show of thumbs. A lot of thumbs ups. Emily, why do you say thumbs up?
Just because if it's continuous, it has to be differential.
Well, in Calc 1, we learned that differentiable functions always have to be continuous. But you could have functions like the absolute value function that are going to be, say, continuous at 0, but not differentiable there. Because a big moral of Calc 1 and 2 is spiky things are bad. Spiky things poke you and hurt you. And also the slope kind of approaches two different values from the left and right, so there's not like a single slope at x equals 0, say.
So if there could be a function that's infinitely spiky, it wouldn't be differentiable anyway.
Can you have a function that's infinitely spiky where you have a spike at literally every single real number?
I don't think so, which is why I think this is true, but.
Sorry. Turns out, if I had a box of continuous functions that are continuous everywhere and I pulled out a random function from that box, there would be basically 100% probability I'm going to pull out one that's differentiable nowhere. Similar to number 6. This one is very hard to find an example though. And this is actually going to be one of the last things we do this semester, is try to find a formula for how would you even create a function that is continuous everywhere but differentiable nowhere. And I'll give you a hint as to how we do that. Power series. We're going to define a series of we're going to be adding up a bunch of functions that get spikier and spikier and spikier and spikier. And the sum of these infinitely many functions is going to eventually be something that is infinitely spiky. The spikiest of functions. But that one we're not going to see for quite a while still. So finally, how about number 8? All infinite sets of numbers have the same size. Seen a lot of thumbs downs. Lydia, what was your thoughts there?
Well, we're talking about like the integers
Mhm.
infinite set, and so with the real numbers like include the integers and then some. So that was my logic there.
Okay, so you're saying the integers and the real numbers are two infinite sets that have, but they have different sizes? That is correct, but not for the reason that you gave. Because you can have two sets of numbers, one is inside of the other, two infinite sets that have the same size. For instance, if I have a set that only has positive integers, and a set that has both positive and negative integers, these sets have the same size, even though very clearly every number in the first set is in the second, but not vice versa.
If I can even include my words. If you take the power set of a set, then, this is how I remember it being proved, then the power set has to be bigger. Because at the very, very minimum, it includes every single individual entry and also the null set. So if you take the power set of an infinite set, it must be larger.
That is true, but not for the reason that you gave. And I'm not going to go into great detail as to why that is, but that'll be something. That's Cantor's theorem. That's something we'll actually be proving in a couple of weeks. Turns out there are infinitely many sizes of infinity. Dr. Gersel, what on earth does that even mean? That's going to be something we explore in probably a couple of weeks from now. So how did I phrase this? All infinite sets of numbers have the same size. Turns out the answer is false. And Lydia, the two sets you gave, the integers and the real numbers, in fact, are an example of that, where the size of the set of all integers is strictly smaller than the size of the set of all real numbers. But proving that is not as simple as just saying every integer is a real number, but not vice versa. There's the way proving that it actually takes a fair bit of trickiness. So any questions or comments about any of these things that we've discussed? Yeah, Matthew.
So the one we just talked about with infinite sets of numbers having the same size, is that have any connection to like L'Hopital's rule with like,
How so?
I always think of like L'Hopital's rule when you're doing limits, you're like kind of comparing like two functions and it just kind of like, they're going at different rates almost. Is that like the same thing where you can, like one is going at like a faster rate than the other, like the sets?
That's, how do I describe this? That's less related to the size of different sets and more related to the size of like the rate at which functions grow.
Okay.
But you're absolutely right in that you can have two functions going to, you can sort of draw parallels there in that you can have like two functions that are going to infinity, but one's going twice as fast as the other. So if you divide one by the other, you still get two. So like for instance, if we were taking a limit as x goes to infinity of say, I don't know, x cubed over x. You know, both numerator and denominator are going to infinity. The numerator just happens to be going so much, much faster than the denominator. You can either use L'Hopital's rule on this or just literally simplify, get x squared over 1, and say, hey, that's going to infinity. The numerator is growing much faster than the denominator. And so you could talk about having two different functions going to infinity, but the rates at which they're going to infinity, one's going, dare I say, infinitely faster than the other. It's not really related to that per se, but you could draw similar sorts of parallels in this case when you're talking about different sizes of infinite sets it's going to turn out. For instance, the set of all functions from R to R and the set of all functions from R to R that are nowhere continuous and the set of all functions from R to R that are continuous at least one point. First of those sets is much, 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 much larger than the second one. Which is why you can draw that sort of 100% probability of pulling out a nowhere continuous function from that box of all functions from R to R. Anyways, I wanted to kind of do this activity to sort of give you an introduction to what are the sorts of questions we're going to be looking at this semester. Because I've kind of been doing a lot of hand waving and being imprecise for my answers to almost all of these. But these are the sorts of questions that we are going to be looking at in great detail in real analysis. How do you compare infinite sets? How do you prove a function like this is nowhere continuous? How can you possibly construct a function that is nowhere differentiable and yet somehow still everywhere continuous? An infinitely spiky function. These are the sorts of things that we're going to be looking at as the semester goes forward. Any questions or comments before we start something new? Alrighty, in that case, got some more packets for you all. So, I'm going to be doing a lot of this as the semester goes on, passing out like little note packets. Typically what I'll do in these packets is I'll sort of have like a skeleton of the notes for a particular class, like I might write out some theorems but not include the proofs, etc. I do this because it helps me keep organized with my material for the class. And if you would like to use these to take notes on, you are welcome to do so. But if you would prefer to just keep all your notes in like a notebook or something and just not use these packets, that's also perfectly fine. It's up to you if you want to use these. You're never going to have to turn any of these in. I'll give you a hint. You know you're going to have to turn something in if it has a spot for your name on it. But if not, it's something for you to keep. So, for us today, we're going to talk about our different infinite sets for the semester. Because that's going to be a big, because these are going to be sets of numbers that we're going to be referring to over and over and over again. And all of them are going to be kind of using these sort of bubbly uppercase letters as symbols to kind of represent them. So if we start out with n, what do you think the set n is? It's a set of numbers. In fact, it's an infinite set of numbers. Does anybody know offhand what numbers are in this particular set?
It's positive integers and I think also zero?
It doesn't consist of positive integers.
Not zero.
We're going to call this the set of natural numbers. And it's interesting that you're unsure about zero because mathematicians as a whole seem to be unsure about do we include zero in this set or not. Because it differs from person to person whether they would consider zero to be a natural number. Typically I found that in the US, zero is oftentimes considered to not be a natural number. In like in European countries, it's common to include zero in the set of natural numbers. So it's a little bit unclear. For our purposes, we are not going to include zero. But this will be the set 1, 2, 3, 4, 5, etc., going on forever. I have a question. What's that? What are these weird little bracket things that are kind of around all of these numbers? So I write out the numbers 1, 2, 3, 4, 5, etc., and then kind of wrote these swirly brackets around them. So what does that mean, do you think?
Set of numbers that they're all.
And
The start and end of a set.
yeah, basically, these are oftentimes used to indicate you're looking at a set of things. So what we're essentially doing is we're taking the numbers 1, 2, 3, 4, 5, 6, 7, going on forever, and what I like to think of a set is it's basically like a box. It's like it's a collection of things. It's like you're taking all these numbers, you're putting them into a box, and you're saying at n, the set of natural numbers is the box from which you could draw, from which you can pull any number from this list. And later on, and no, we're not going to come up with a formal definition of what a set is, because that's actually really complicated, and I'll leave that for Dr. Gabler in his math logic class. But a set, for our purposes, is going to be like a box, like a collection of mathematical things, like numbers or functions, things from which you can pull individual elements. So when we talk about the set of natural numbers, we're just talking about the set of all of these 1, 2, 3, 4, 5, etc., which for our purposes is not going to include zero, though there are a lot of mathematicians who would say zero is a natural number. How about z? Joel?
It's a set of integers.
Z is the set of integers, indeed. What's this? What's in the set of integers?
All the natural numbers and all of their negative converses.
Yeah, every natural number, 1, 2, 3, 4, 5, etc., all of their negatives, negative 1, negative 2, negative 3, negative 4, etc., and 0. Yeah, so that's the set containing 0, plus or minus 1, plus or minus 2, plus or minus 3, etc., etc. Which again, we can sort of write out in a list format like this. Anybody know why the integers are called z? I mean, natural numbers being called n makes sense, n for natural. And the integer's z and not I.
Does I just look too close to 1?
Actually, that's not a bad guess. It's usually because I is usually used to refer to the irrational numbers. But Dr. Gerstle, why z? There's no z in integers. Z here actually refers to the German word solid, which is the German word for number. And for whatever reason, that's what we use to refer to the set of integers. Now it's the letter z. No, I don't speak German. If you want to learn more about how mathematics is done in Germany, you should go talk to Dr. Volksoff. She's study abroad. How about Q. Emily Rose?
All rational numbers.
All rational numbers. Yeah, which we said before, what's a rational number? Well, it's a number that can be written as a fraction. Or how I'm going to write it, instead of all a over b, colon, a comma b, squiggly symbol, integers, b not equal to 0. Okay. Here's where the notation gets complicated, if you're not used to working with this sort of notation. So, there's a few symbols in here, specifically this one, and also even the colon. They're kind of being used in ways that you may not have seen before, depending on what other math classes you've taken. The colon is kind of a shorthand for satisfying that, or such that, however you want to refer to it. Does anybody know what this symbol is? Emily?
And be an element of.
Yeah, is an element of, or are elements of in this case. So how would I read this set? It's the set of all numbers of the form a over b, that's an 8, not a 9. Numbers that are of the form a over b satisfying the condition that a and b have to be elements coming from the set of integers. And b is not equal to 0, because you don't want to divide by 0. So in other words, whenever you write like a set like this, the set of things that are of this form, you can use the colon, or sometimes you'll see like a vertical bar. There's a bunch of different ways to write this. But the colon here means satisfying the condition that what are a and b? Well, they're numbers that are coming from this set down here, the set of integers. So things that would be in this set would be numbers like 1/3. 1 and 3 are integers, so 1/3 should be an element of the rationals. -5 over 99. Well, -5 and 99 are both integers, therefore -5 99ths should be an element in this set, because it can be written in the form a over b, where a and b are elements of this set right here. Any questions or comments about that? All right, Emily Rose. Why are we using the letter Q to refer to rational numbers instead of, I don't know, R?
Could it possibly be because of the word quotient?
It is precisely because of the word quotient. We don't use R because R is going to be the set of all real numbers. Spoiler alert in the next step. But Q, kind of used for the word, kind of refers to the fact that we're taking a quotient of integers, meaning we're dividing one integer divided by another integer to get elements that are in this set. You can also think, when you see rational, don't think of rational as being that which is capable of logical thought, or however you define rational in your philosophy course. Think this one. It's a ratio of one integer to another integer. So like 1/3 is the ratio of 1 to 3. And so when we say a number is rational, we mean it can be written as a quotient like this. It's in the set of rational numbers Q. All right. If you notice, by the way, each of these sets is gradually getting bigger, in the sense that every natural number is an integer, every integer is a rational number, and it's going to turn out to be the case that every rational number is also going to lie in this set, R, which is going to be the set of real numbers. What's a real number? real number is surprisingly hard to define. But what makes a number real? If you ask Dr. Seifert, most numbers are not real, and he's even if they're in the set of real numbers, I believe he's wrong, but that's just me, and since you're all in my class right now, you have to agree with me for this hour. But what makes a number a real number as opposed to numbers you may have seen before that would not lie in this set?
There are irrational numbers in there?
This is going to include irrational numbers. What's an irrational number?
Numbers that are not part of the quotient.
No-
Or the
Numbers that are not
yeah.
in here?
Yeah.
Okay. So the real numbers are numbers that are in this set and consist of numbers that are in the set and numbers that are not in this set.
Uh,
Does that mean real numbers are every possible number?
no, it's not imaginary.
Ah, not imaginary. Yeah. So this set is not going to include, say, something like square root of -1. That would be an example of something that lies outside the set of all real numbers. But how do we actually define what the set of real numbers is? And for these first two sets, it's easy to just kind of list out like, oh, it's numbers that look like this, or numbers that can be written in this way. It's a lot harder to do that with a set of all real numbers. And I mean, this course is called Real Analysis, so ideally we'd like to know, this is a course where we learn about real numbers, we should probably know what is a real number at some point. So what would be an example of a real number that's not in the set of rational numbers?
Square root of 2.
Square root of 2 would be one.
Pi?
Pi would be another. What's the other one that you've that you see a gazillion times in any calc class?
E.
E.
Golden ratio.
The golden ratio. 1 plus square root of 5 over 2. That would be another one. The square root of any natural number that's not itself a natural number, in fact, would be one of these irrational numbers. But again, it's hard to actually define what is a set of real numbers by saying, oh, it's things that look like this and things that look like this, because what are these things? These don't really look anywhere alike. This is going to be something we actually have to be very careful about and are going to build up to for the next week or so. Because I'm guessing that most of you have a lot of intuition as to what's a real number in your mind. It's something on, say, the number line. But trying to say, okay, what numbers lie on the number line? It's not an obvious task. It's easy to point to an individual number and say, that's a real number, or that's not a real number. But trying to classify all of these real numbers as a whole is quite difficult. I'll say for now, in quotes, all numbers on the number line, and then add, very hard to be more precise than this. So finally, how about C?
Is that all real numbers, imaginary, and complex, any combination?
Yeah, it's going to be the set, in fact, I'm going to take one word that you said. It's a set of all complex numbers. C for complex in this case. And how can we write like the general form of what a complex number might look like?
A plus bi such that A and B are elements of real numbers.
It's a combination of a plus bi, where a and b are real numbers, and I is going to be, what's I?
-1.
Does -1 have a square root?
No, not unless you define it.
I is going to be a number that satisfies when you square it, it is equal to -1. So here's the thing about I. I gets kind of a bad rap. And I think I spoke that sentence with proper English. I gets a bad rap. Me, Dr. Gerstel, Isaac gets a bad rap. Here's a question. Square root of 2 is a real number. I is not a real number. Do either of these numbers exist any more than the other one? This is not a question, by the way, that has a correct answer to it.
Yes, I think square root of 2 exists a lot more because, I mean, if you think of rational numbers like pi,
Mhm.
I mean, you can see a circle and like you just know that that has to be real. Whereas like I is like where you, like some electrical circuits have it with like currents that we kind of like made up formulas for. Like,
Yeah.
that's kind of gimmicky.
I mean, I could draw square root of 2 pretty easily right now. Boom. Right triangle. Right triangle. This has length 1 and this has length 1. This has length, well, it has to have some length. I can define square root of 2 to be equal to that length. If we want the Pythagorean theorem to say be satisfied. Can we draw out I? Sure, why not? Boom, I just drew out the number 2 plus 3i in the complex plane, where we have a real axis and an imaginary axis. Actually looks more like 3 plus 2i. Square root of 2 shows up in a lot of useful formulas in like physics and math, etc. But so does I. So Matthew,
No.
do you still claim that like you think square root of 2 has more existence to it than I does?
Yeah, it's like right that you just kind of made up a whole axis to try to get I involved. Whereas like the other one is just coming up.
Okay, but I just made up a triangle and to get square root of 2 involved.
A circle in like just nature has pi like in it.
Are there
Like,
circles in nature?
There's definitely contours and stuff that have irrational numbers.
Sure, but I could I could write an imaginary contour just as easily.
Yeah, you could, but it's not going to show up in like the real world.
I argue that the real world does not have perfect circles.
Wait. I mean, that's fair, but also at the same time, would you? There's probably honestly continuous, like infinitely differentiable, like things where irrational numbers are going to show up, and imaginary numbers, like the only things where they show up are a lot of man-made things. And also, like when I just think of parabolas and trying to find roots, like the whole point of I is you're trying to force like a root to exist when it's like not even existing.
You try to force a root to exist when it's not even existing? All right, well, let me ask you this, Matthew. Instead of I and square root of 2, how about square root of 2 and 10? Or do either of those exist more or less than the other one?
No.
You claim those are equally existing?
No,
No?
no, because the way I've always, I don't know, different levels of existence. You can't have square root of 2 objects. It's not possible, but I can have 10 marbles.
Okay, so you can have some marbles sitting in front of you, and you can make the argument that aha, I have 10 of them. How is that the number 10? Is the number 10 floating around that set of marbles in a way that you can say this set of marbles is 10, the same way that this set of marbles is red, or this set of marbles is made of glass, or what do you all think? Heard a lot from like this column right here. I'm interested in hearing from the rest of the class. Emily?
Well, square root of 2 is always going to be an approximation, so you're never going to.
An approximation? What does that mean?
Because you're never, like, starting with
If you were to try and write out a decimal for it, you mean?
Yeah.
Yeah, if you try and write out a decimal for 10, you can write it out as 10. If you try and write out a square root of 2, you could get, that's 1.414 going on forever. On the other hand, I you could write out a decimal approximation for as I. So is I more real to you than square root of 2 is?
I don't know about that. No comment.
A comment on that? Dr. Gerstle, is this whole class just going to be standing around philosophizing like this? No. No, we're going to get into much more nitty-gritty detail, but I want to ask you this question because this is something I feel like numbers can get a very bad rap in mathematics, like imaginary numbers versus irrational numbers versus like numbers from kind of the most standard set, the ones that you're introduced to the earliest, numbers like the counting numbers or the natural numbers, 1, 2, 3, etc. But I assure you, I and say Dr. Seifert, who I've talked to quite a lot about this, could get into could go on for days and days about whether any of these numbers exist, or whether none of these numbers exist, or whether some of these numbers exist. So when you see I and you think, oh, it's an imaginary number, I don't want you to be thinking imaginary as in something that's fake, something that doesn't actually exist. I want you to be thinking, because it's a little bit of a misnomer. There are arguments for why something like I may or may not exist any more than square root of 2 does, or 10 for that matter. But really, it's a matter of perspective, or a matter of philosophy, I would say. You could ask a philosopher. If any of you talk to Dr. Church about this sometime. He probably has some interesting views. But complex number for our purpose is going to be what you did if you take real number plus real number times this I thing, which is something that we're going to say has the property that if you multiply I by itself, you get -1.
So could B be 0 here so that you could just have A plus 0I and then
Sure,
it also includes just the set of all real numbers?
sure.
Well,
So I would say, for instance, 10 is an element in the set. Because you can write 10 as 10 plus 0i. 10 is a real number. 0 is certainly a real number. So any real number is automatically going to be included as a complex number by just setting the b term equal to 0. Any questions, other questions or comments about how we're defining these sets? So how do we know irrational numbers exist? Emily, you said you look at square root of 2 and it has a decimal expansion that goes on forever. How do you know it goes on forever? How do you know you just haven't looked far enough out yet? Maybe after the 1 billionth digit it finally ends.
You can prove by contradiction.
Proof by contradiction. Ooh, pull out some reductio ad absurdum, huh? Let's take a quick look at that in our last few minutes. So, let me set the scene for you. It is the time of the Greeks, and specifically it is the time of Pythagoras. So Pythagoras, named from the Pythagorean theorem, although he was not the first person to come up with it, or to even prove it. The Pythagoreans were basically a cult of like ancient Greek mathematicians that sort of kind of worshipped the natural numbers like 1, 2, 3, 4, 5, etc. And we go around saying things like all is number, and love the natural numbers, and love the fact that every number could be written as a ratio, as a quotient of natural numbers or integers. Until this one guy came along, Hippasus of Metapontum, and said, hey, this number, where if I draw a right triangle like this, and this has lengths 1, 1, and whatever, this has to have a length that's not a rational number. It's impossible for it to be a rational number. And what did the Pythagoreans do? According to legend, they killed him. They threw him off of a boat, is how the legend goes. And obviously, there's no way of knowing if that's actually true. It's a fun story about how this guy came along, proved square root of 2 could not possibly be a rational number, and then was killed for it. How math can be dangerous. So, let's see if we can prove this. Square root of 2 is not in the set of rational numbers. Emily Rose, you had an idea for how you would go about showing that. So what was your idea for how you could show that it's impossible for square root of 2 to be a ratio of 2 rational numbers?
So if you did proof by contradiction, you'd start by saying, if it is a rational number, then the square root of 2 must be equal to some fraction p divided by q, where p and q are integers, and p and q have no common divisors.
And then you go through a logical argument that eventually shows but p and q do have to have a common divisor contradiction.
Yeah, and then, okay, so I'll cancel that, and then just start over and it loops it.
Yeah. Essentially, this uses a very common proof technique that we're going to be seeing a lot this semester called proof by contradiction or reductio ad absurdum to prove something, which is often used to prove a negative, like prove square root of 2 is not in this set. There's no way to write square root of 2 in the form integer divided by integer. Is you suppose you can do that. Suppose square root of 2 can be written as a quotient of integers, and then you show that a logical contradiction has to somewhere occur. If you're in the philosophy department, they'll call it reductio ad absurdum. In the math department, we call it proof by contradiction, more commonly. But we'll do that proof on Monday, in the interest of time. So that's going to do it for today. When we come back on Monday, we'll prove this fact and then start looking at what are our actual axioms of the real numbers. What are properties for each of these 5 sets that some of these sets satisfy but not the others? And we're going to see if we can come up with a list of mathematical properties, interesting properties, that the real numbers satisfy but none of these other 4 sets are going to satisfy from the front page. So with that, hope you all have a good weekend. I will see you all on Monday. We will get into our first proof of the semester.
I'm lucky I haven't done much proofs before.
Yes, I can tell. And that'll definitely help out a lot. But.
It has been entertaining. This class has been on the horizon for me for a while.
Mhm.
And I keep asking my mom, who was a math major, what is real analysis?
Mhm.
And her answer has always been proving calculus starting at arithmetic. Which is a good enough answer, but never really cleared it up enough. So I've never.
I mean, to be fair, we are going to be doing a lot of that. It's not like an inaccurate answer, but there's a lot more to it as
There's a
well.
lot more to it, and I was never able. She kept telling me to just go look at your textbook. I was like, I don't want to look at your textbook.
So it doesn't include lots of.
See you on Monday.
Yep, have a good one.
You too.